Microphone is on.
Microphone's on. Recording.
Recording is on.
Recording is on. All right.
You did your job. You reminded
We
me.
have the technology. My demo system, unfortunately, is not doing too well. But fortunately, I have a backup. I have videos. So, all right. Hi, everybody. I'm Mark Nelson from Oracle. I've been at Oracle for 19 years and 6 days.
Not that you're counting.
So looking forward to that special present next year. Special Starbucks coffee card.
Yeah.
Doug Drechsel is with me. He's been at Oracle for 340 years. Not true. So we're both
close.
from the database organization, and we work with developers, mostly with microservices and AI related technologies. So today I'm going to talk about a tool that we have, an open source tool called AI Optimizer and Toolkit. And also I'm going to talk a lot about just sort of generic, I was going to build AI stuff. I don't know how much everybody knows about AI and GenAI, so hopefully there will be something of interest that you didn't know. If you're all experts already, then it might be a little boring, but we'll see how we go. Okay, so I'm going to start with GenAI challenges. So, you know, everybody out there is talking about chatbots and AI assistants and agentic AI systems and all this kind of stuff. And if you go look on YouTube, you can easily find hundreds of videos of people who show you how you can build one of these things in 5 minutes or 6 minutes or so on. There's literally hundreds of these things, and here's a little sampling of them here. But, you know, it's actually a little bit more complicated than that, as I'm sure you all know. Like, all these things come along and there's a big hype and everything's so easy, but, you know, in reality, it's a little bit more complicated than that. So what really defines enterprise quality, I guess, is what we're going to talk about. So this is an article that I really like. It's called 12 Famous AI Disasters. It was in CIO magazine, and I picked out a few little snippets here of some of the things that they talked about. So it was people implementing AI-based systems who maybe didn't do all of the due diligence that they maybe should have done and had problems. Like McDonald's, I think if I remember, it gave somebody 10,000 hash browns or something. I can't remember what it was. There were things where chatbots lied about things, or that there was a healthcare one that was like making a racist decision, for example. So all kinds of problems. And these things are very embarrassing for organizations when they happen, and nobody wants to put an AI out there and have it do something stupid that embarrasses you or gets you into some kind of, you know, legal trouble even. Gartner made an interesting prediction that 30% of GenAI projects would be abandoned after proof of concept by the end of this year. Now, somebody who will remain nameless told me that this looked like an AI generated image, but this is the real person who really wrote this report. She exists. She works for Gartner in Asia Pacific. So what are some common challenges of building these kinds of applications? Somebody went and put builds into my slides. This is the problem with SharePoint. People can go in there and change stuff when you're not looking. So, okay, there's lots and lots of different models, large language models and diffusion models and other kinds of models. And, you know, how do you pick the right model for a particular task that you want to implement? That's a challenge. And then all these models have parameters that control how they behave. So choosing the correct values for the parameters is also something that you need to do, right? The default parameters might not be right for your particular use case. And also things like memory, like how do you keep track of the conversation that's already occurred up to the point where the last interaction just happened, you know? Because by default, these things are they're stateless. They don't know anything about what happened in the past. So you need to have a way to capture the memory so that they know what's going on and have context. Another, you know, super big problem with LLMs is what we call knowledge cutoff. So when these models are trained, the people, just let me take a quick, how many people would say that they are like really experts in terms of LLMs and generative AI and AI in general? And many people know what a GAN is.
Today.
Okay. Many people know what a neural network is. Okay. Many people know what a matrix is. Okay. So, all right. Okay. I'm just gonna go with the level that I had, and hopefully it'll be okay. So a model is like a mathematical representation of some real world phenomenon that behaves like it, but it's simpler, right? So these, sorry, I'm not supposed to move. So in generative AI systems, we use large language models for text or other kinds of models for images or video or whatever it might be. So these models are trained on a very, very large set of data. That's called the corpus. Usually it's publicly available data off the internet, and there are well-known data sets that are used to train these things. So the large refers to the huge amount of information that is used to train these models. And basically what they're doing is predicting, what would be the next word, for example, what would be the next token. So if you said to it, like, the cat sat on, it would probably say, the mat, because that's the most probable next words to finish that sentence, okay? But the problem is when you train them, there's a finishing point, right? So anything that happened after that point in time, it has no idea about it. It's never seen that information. It doesn't know what happened. So there's a cutoff, there's a knowledge cutoff, and it doesn't know anything after that. Also, because they're trained on public information, I guess people really want to use these to build things to help to interact with their customers or suppliers or employees. They need to have access to private company information, like policies, or maybe they need access to your systems to look up things like, maybe you want to have one that your employees can ask, what's my last benefits payment for my healthcare or whatever. It's got to be able to go look that up. So none of these models have access to any of this private data. So those are some challenges, and we'll come back to these and talk more about how to deal with these. Another big challenge is the quality of the corpus, the information that you feed into the model to train it. I'm sure you've all heard the expression garbage in, garbage out, and that applies here as well, right? If the information you use to train a model is not very good quality, then the model is not going to do a good job. And then there's a bunch of other things. So when a user asks the model a question, so say for example, they say, I don't know, how much is the fee for a check account or something? It's not really very specific question. I mean, what's the model supposed to do? It might go like, well, we have 10 different check accounts and they all have different fee structures and blah, 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 whatever. So, the quality of the question that is asked has a big impact on the performance of the model as well. So there's techniques like we'll talk about later, like rewriting the question for the user to make it more specific, or guessing what they're really trying to ask about and stuff like that. Another challenge is domain-specific language. So this is really important in like healthcare and banking, finance, legal, some industries like that, where either the model just doesn't know the terms that you're using because it hasn't been exposed to them, or they're like common everyday, English words that mean something completely different in the context of the industry that you're working in. So that is a challenge. Sorry, I'm going to try and stop moving with the camera. That is a challenge.
It tracks you a little bit.
Okay, cool. I can't remember why I use the result right away there. Somebody else might have added that to my slides. So one way to deal with this is to fine-tune a model. So fine-tuning a model is when you take a model that's been trained already on a huge amount of data, and then you introduce new data, like your private data, for example, maybe all the documents about your products and so on. And you continue training the model. So you're adjusting the model weights and so on, okay? Which means the model actually learns about this new data. Learns in, it doesn't really learn, learns. It learns about this new data. And the challenge with this is it is super expensive to do. Like we're talking millions and millions or tens of millions worth of dollars worth of GPU resource to do fine tuning of a model with any reasonable amount of data. Okay. Plus, the data has to be good quality. You've got to have people who know what they're doing, etc. So it's a very, very expensive to do. And typically you need to use a huge amount of data to really be able to train the model effectively. You know, if you fine tune on a very small amount of data, you don't really get a very good result. You really need a very large amount of samples for it to see, for it to learn effectively. And you really need a human expert who can review the output and give feedback, which also is expensive because you've got to pay those people. And typically the people who know the right stuff are not, you know, inexpensive people. They're more, you know, higher paid resources and stuff like that. And it takes a long time. Okay, so overall, it's a very expensive exercise. Yep.
Do you ever expect that you would get the same answer for the same question back every time?
Well, yeah, you can. So we'll talk about this. One of the parameters of a model is something called the temperature, which we'll talk about later on, but it controls how creative the model is. So these models are non-deterministic in nature, right? They're probabilistic. They're just doing math, basically, to come up with the next most probable answer. But if you tune the temperature to a very low value, it is possible or probable that you will get the same answer multiple times to the same question.
In that mode, could you create a suite of tests to see if it is coming up with the same answer for a test suite?
You could, but then you might not want to have that parameter tuned that low in real world usage because it might not have enough creativity to be able to give a valuable answer to people. So I will come back to that. That's a big topic for sure. So let's go over some concept and foundation stuff, and then we're going to talk about the tool. So generative AI is a type of AI that can create original content in response to a user's request. So AI has been around for a very long time, since like 30s, 40s, 50s, I think it's fair to say, so a very long time AI has been around. Even before we had digital computers, people were talking about AI. Machine learning is sort of a subset of AI, which uses algorithms that are able to learn and tune parameters to improve performance. And generative AI deep learning is a subset of machine learning that uses neural networks with many hidden layers to solve complex sort of nonlinear problems. And deep learning has been shown to be extremely successful. And it was really invented, I think, in the 60s, 70s. A lot of the really important papers were written, but they didn't have the volume of data or the compute resource to be able to actually implement it. So it was just theoretical. And it's only really in the last 10 years that we have had access to enough data and enough compute to be able to implement this. And the big breakthroughs we've seen, we all know about ChatGPT, for example, which was a big breakthrough in that. And Google had a big breakthrough called the transformer architecture a little earlier than that, which GPT built on top of. So it's only recently that we had, the data and the power to actually implement these things. And then generative AI is a subset, again, of deep learning that is focused on creating new content. Okay. So generative AI models are deep learning models, which are machine learning models, which are a type of AI. They are pre-trained on a large amount of data, as we talked about, to identify patterns and relationships between the data, so words or images or whatever it might be. I'm going to talk a lot about language models, but obviously there are image models and video models and all sorts of, but just for simplicity, I'll sort of focus on language models. These language models provide a chat interface, so you kind of talk to it, rather than doing a search or whatever, you have a conversation with it. This is an example here of asking a model to explain what generative AI is. Okay. model choice. So there's lots of models. As I said, large language models. There's also something called small language models, which is something that I'm particularly super interested in. So large language models have a huge amount of common knowledge, okay? And they can reason, they can follow instructions and do things like that. Later we're going to talk about something called retrieval augmented generation, or RAG, which I'm sure you've probably heard. And an interesting question is, do you need an LLM if you're using RAG? And I think the answer is no. A small language model can reason just as well as a large language model. And if you don't need it to have all of that common knowledge, because the knowledge is coming from your private data, then you really don't need to run the biggest, most expensive, fanciest model, to get the same outcome. But anyway, there's lots of different models. There's new models coming out literally every week. There's hundreds and hundreds of these things available. Some of the main families of models are the ones you've probably heard of, the GPT models, that stands for Generative Pre-trained Transformers. The Llama models that come from Meta. Claude has a family of models called Sonnet. Cohere have a family of models. So there's lots and lots and lots of these models, okay? Some of them are trained for a specific task. So some of them are very good at answering questions. Some of them are very good at following instructions. Some are good at extracting entities from a text or summarizing a text, okay? And some of them are sort of general purpose models that are good at a number of different things. There's also diffusion models that are good at creating images, and there's models that are good at other non-text related stuff too. And there's multimodal models that can work with text and images and video and everything in the same model. There's also, models that are very good at writing code, like Grok Fast 1 and Claude Codes has a model that's very good at writing code, for example. So there are also models that are very good at looking at a medical image, like an MRI image, and detecting whether or not it has cancer, and so on. There's models for all kinds of specialized tasks, okay? So you can see how choosing a model might be a problem, right? There's literally hundreds of these things. And if you have a particular use case that you want to implement, choosing the right model is not necessarily a simple task. So we'll talk about databases a little bit. Databases are great at storing business data like numbers and strings and dates and stuff like that. But typically they haven't been very good at handling unstructured data like images and documents and videos and all that kind of stuff. So, the concept of a vector database appeared, I don't know, a few years ago, which makes it easy to capture the semantic meaning. Sorry, I'm trying to move. Semantic meaning of things. So let's talk a little bit about vectors. A vector is a sequence of numbers. It represents the semantic meaning of something, like a piece of text or an image or whatever it might be. And you can create a vector by using another kind of model called an embedding model. Okay? So there are special purpose models that create these vectors, these vector embeddings that represent the meaning of a thing. Oracle does support vectors like many other databases, obviously. So here's an example. Now, in real life, vectors that are used in common models like GPT and Llama and so on have hundreds or thousands or tens of thousands of dimensions. So then when you look at the vector, there's thousands of numbers in the vector, okay? But it's very difficult to visualize that. So I'm gonna, just for now, imagine that a vector has 2 dimensions, okay? And we'll scale it up later in our heads. So imagine that one of the dimensions is dogness, like how much of a dog is this thing? And the other is largeness, okay? How large is it? So here you see a German Shepherd, I hope. And you can see it's pretty large and it's very much a dog, okay? So its vector is like pointing way over here. Very large, very much dog. Here's a, whatever that is, Saint Bernard, the whiskey dog. And it's also pretty big, and it's also very much a dog, right? Now a wolf is not a dog, really, but all dogs are descended from wolves, right? So there's a relationship between dogs and wolves. They are similar.
Canine.
Yeah, exactly. And they're pretty big. So you can see it's pretty high and large, but it's not so close to the dogs. You know, it's kind of like a dog, but it's not a dog. And then down here you see a tennis ball, which is not big and it's not a dog at all. So its vector is actually in the complete opposite direction to the dogs. Okay, yep.
What strikes me is what does the negativeness of similarity mean? Right? So like
It means not similar at all. Yeah.
no, I know. But more not similar than it's like more not similar. It's
Yeah.
Like which is less similar to a dog?
That's it. Okay,
A
that's
tennis
a
ball or a watermelon?
yeah.
I understand similarity.
Right.
Seems sort of it feels more well defined.
Yeah.
But the non-similar is like, well, everything else. It's like
Yeah.
it's so large as to be almost meaningless.
That's a super interesting question, because what the similarity mean is the other question, right? So in vector databases, when you do vector comparisons, there's lots of different ways to determine how similar a vector is, right? So one is, you know, how close are they to each other? Like you can do a dot product to find out the distance between them, for example. Another is called cosine similarity, which just measures the angle here. So these two are very similar because this is a very small angle. If they happen to be here rather than here, it wouldn't matter. They still would be similar, right? Because the angle, and here the angle is almost 180 degrees, so it's very dissimilar. So cosine similarity, which is very, very good for text, doesn't consider the distance or the magnitude. It's only the difference in the angle, the spread. So yeah, I think that like comes a lot to like when you're saying like, what does it mean to be unsimilar? Like, what does it mean to be similar is another question, right? Because there's lots of different ways. There's literally lots of different ways to calculate how similar a thing is. Okay.
I would
No,
just
I was
like to
actually
follow
not
up one
asking
thing
Yeah.
about
there.
the similarity between things. I was thinking like, well, you've got positive dogness. I'm like, what is negative dogness?
Yeah.
That's the part that confuses me.
Yeah.
You know,
Yeah.
like negative largeness or any of these things.
Right. Right.
Because they seem to be like not defined.
Yeah. Exactly.
Whereas
So
there's
in
I
real
just
life,
wanna address
yeah,
that
go ahead.
too. You
Go
know,
ahead.
there's a lot of, and really, this is where the magic happens, in my opinion, right? The algorithms that make these huge vectors to determine similarity. So I definitely struggle with what you do, because that's magic. And there's different models that do these vectors, right? Like
Yes.
I forget
MX,
which one we
VAI,
use. Yeah,
embed.
yeah. So
Yeah.
there's different models that determine the similarity, different lengths of the vectors, right? So yes, it's magic. You have to factor into those models. There's some that'll do it with video. There's some that'll do it with images. There's some that'll do it with text. But yes, I understand. And I'm just saying, I think that's where the magic is. And there's some really smart people that make these algorithms that do these vectors, as you can see evidenced by every time you talk to AI. And it is amazing, in my opinion.
So you could imagine, you kind of have to scale it up in your head. So imagine there's a cluster of dog kind of stuff here. And maybe here there's a cluster of cats. And maybe here there's a cluster of houses. And here there's a cluster of trash cans. And they're all sort of spread out in this space somewhere. Like they all occupy their own space. But, you know, just because the trash cans are here and the dogs are here, it doesn't really mean, I mean, trash cans are not dogs, they're something else, but it's not really like negative dogness exactly.
And
You know what I mean? You know what I mean?
and you have to keep
It's
in
just a
mind you're in
different-
a
different
1,000
little
dimensional
cluster.
They
space.
could be related by
Right.
somehow. No,
Exactly.
Not
Yeah,
negative. In
Yeah.
the graph, there is negative. I mean, your
Yeah,
graph is
yeah.
negative, and then it kind of has me think like, what does negativeness mean? in
Right.
this
Yeah,
kind of
yeah. No,
And you've got to remember, this is a
I hear you.
massive simplification, right?
Yeah, yeah.
Yeah.
In real life, there would be, like in a model like ChatGPT, thousands of dimensions, not two. And none of them have a simple concept like dogness, right? None of them, there's, when you look at the embeddings that are created, you couldn't look at it and go like, oh, the third thing means how much of a dog this is. Like there are things that mean nothing to us. It's
It's still like dogness is spread out over 50 dimensions.
right, exactly.
Yeah.
Like
Yeah.
when you look at
Yeah,
genes,
in
you know, like
some
which
way.
gene says you have black hair? It's like, oh, it's these 17 genes. It's that sort of thing, right? You know, they're
And my fetal environment. Too.
exactly, yeah,
Well, I mean, so when I saw this picture, the first thing that came to my mind is that it actually that's a solution by itself. So
Yep.
if I had a bunch of photographs, then I'm going to teach the generative AI algorithm to generate other photographs.
Yep.
And there's an algorithm that's going to put vectors on everything.
Yep.
Right. For me to say, can you please output your vectors and for the list of photographs I gave you, tell me your dogness of it.
Yeah.
You know, that's a way of sorting images that
Yeah.
that I might use for storage or something.
Yeah. Image vectors are actually done differently. They're done with the pixels and extracting. They do like what's called principal component analysis to reduce the number of dimensions. So you see the images become kind of blurred and stuff, but they figure out like, you know, a picture of a dog has got two eyes, two like little round dark circles in it that represent eyes, for example.
If you've got a head-on shot.
Exactly. Yeah.
Right.
So this is more like a text. Think of this as text, but you know, image diffusion models are a little different the way they create the vectors. But you know, it's the same concept, but it's not the semantic meaning. It's based on the colors of the pixels in the image, for example, and the density and stuff like that.
But you're still saying that there's an algorithm that generates these vectors.
Yes.
It's not a person.
Absolutely.
A dog is vector to this picture.
Yep. It's another model, a specialized model that we call an embedding model, which is used to take a piece of text or an image or whatever and turn it into a vector. Yeah.
So it's some magic that makes it hash.
It's just math. It's not.
Yeah.
I mean, it's not really magic. It's just. It's like
ask him to explain it to you. It's magic.
I can. I can explain it to you, and I will, but afterwards.
So it's sort of a hash of the.
It's a lot of calculus.
Yeah.
It's if you know how a neural network works, you have like inputs. You have an array of inputs. You have an array of weights. You have a bias, and you have multiple layers that they pass through, and you basically train the model on lots and lots of samples with labeled samples so that you know what the output should be, and then you tweak the weights and the bias in each level until you get to the most effective model that comes up with the result that you want most of the time. So it's not really magic, it's just math and machine learning. But yeah. Okay.
Well, so does it start with the annotation, right? Like you have
Yep.
to annotate.
When it starts, yeah, you need to have labeled data.
If you don't accurately annotate,
right.
This is a cat and this is a dog.
Exactly.
Like, so you might have like 10 or you might have 100 annotations to
Yep.
that picture.
Yeah.
Because it could be under all these different categories.
Exactly.
Right, and then that's how it gets.
Yeah. Image models are typically trained with labeled data, meaning you have a thing that says this is a cat or this is a dog or whatever. Exactly. You know, and
it's part of a farm.
Yeah. So when you start, it's just going to guess. It's going to like, oh, that's Doug. Okay, no, that's a dog. And then the next time through, it'll be a little bit better. And they go, I think that might be a dog. You know, and eventually when you run it through enough iterations, you'll get to the point where it'll come up with a model that can reasonably reliably predict, you know, or categorize what the images are. Yeah. Okay, let's move on. So there's different ways, as I said, to create these vectors. I'm not going to go through that. You can do it like in the database or externally or all that kind of stuff. So as we talked about, the main operations that we do on vectors is calculating the distance between them. And there's lots of different ways to do this, as I mentioned. One of them is called the Euclidean squared distance. One of them is called the Euclidean distance. There's the Manhattan distance. There's the dot product. There's the cosine distance. There's lots and lots of these. Okay. So, for example, Euclidean distance is you just say, well, what's the difference between like, you know, the 3 and the 2 is 1. The difference between 1 and 6 is -5, and so on. And then you add them up, and you go like, oh, that adds up to whatever 7. That's the distance. Okay. And then you and so on. So you might do that. You might take the square root so that you get the distance in a straight line, or you might leave it as squared, which means you don't have to do the square root, which means the calculation is a lot faster. Because imagine like here, it's not a big deal, there's 4, but if you had 10,000 dimensions, taking 10,000 square roots is a big deal. So if you just leave them as a square, you save half the work, right? And so on. So there's a bunch of different ways to calculate the distance between these things. And basically, the smaller the distance, the more similar they are in terms of their semantic meaning. Okay, So as I said, the actual qualities measured by the dimensions are abstract. They're not things that you could put a word on. There's lots of different ways to measure similarity. This slide is kind of a little bit old now. I wrote this maybe a year ago. Models now have even larger number of dimensions, in the tens of thousands and so on. Okay. Blah, blah, blah. So in Oracle, we have our vector database capability. It's very fast and allows you to create a vector index. And there are different kinds of vector indexes, and other databases do this too. It's not just Oracle, but Oracle just do it a little bit better, obviously. So when you have a vector database, you basically have think of it as a table with all your vectors in it, right? So if you want to find the nearest vector, so you want to search for something that's like a Saint Bernard, right? What are you going to do? You have to go through all of the other vectors and calculate the distance. So if there's 20 million of them, you've got to go and calculate the distance between 20 million different pairs of vectors, right? Which is expensive. So an index is a way to improve that. There's different kinds of indexes. There's one interesting one called a hierarchical navigable small world index, which basically has clusters of things that are close to each other in separate little graphs that are linked together into a huge hypergraph, essentially. So if you need to find something that's like close to Doug, I would get the graph that's this table here, and I would search this one, right? I wouldn't bother looking at that one over there because, she's way, way over there. She's obviously not going to be close to him. There's no point even searching those graphs over there. Vector indexing is an interesting technology. This is a picture of a hierarchical, navigable small world index. Is what it looks like. So you can very quickly get to the point where you want to be and just look at the things that are near you. So this means rather than doing those 20 million calculations, we can maybe do, 100 calculations. So it's obviously much, much faster and more efficient.
By the way, do those
Yeah.
little subgraphs, do they tend to partition the data, or they
Yes.
overlap a lot?
No, they're unique.
They're
Yep,
partitioned.
they're clusters. Yeah. In Oracle, we do also allow you to mix and match. This is something that is probably, I guess, unique to Oracle. I don't know of other vector databases that do this because for us in Oracle, the vector is just another data type. You can have a column in a table that's a vector, for example. So you can mix and match. So you can write a query, say like, give me, customer name, product, blah, 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 and also include, where something or another vector search, where vectors like this. So you can take semantic similarity searches and combine them with like the kinds of things that you would do in SQL or whatever. So that's kind of pretty interesting capability, a hybrid search. And also in Oracle, we do all of the normal features apply to vectors as well. So you can run them in a cluster of databases or a sharded database. When you do a query, it can be parallelized. They're transactional. You have the security and all that kind of stuff. So all the normal things sort of apply. If you happen to have an Exadata, does anybody work for anyone who has an Exadata machine that you know of? No? Okay. Exadata is like this machine that runs Oracle databases. If you happen to have one of those, the vector searches scale transparently across all of the nodes so that they run very, very fast. They can be offloaded to the storage cells, which means that they don't consume any CPU on the database servers, and so on. If you have a sharded database, the vectors can be geographically distributed across the shards, and the queries can run across all of the shards and so on as well. Okay, so let's talk now about something called retrieval augmented generation. So before we talked about fine-tuning and how it's super expensive and painful, right? So a very, very popular technique, I'm sure most of you have heard of it, is called retrieval augmented generation, or RAG, which is a different way to address the problem. And it relies on vector databases, which is why I've been talking about vector databases. So what you do here is you take your private data, your corpus of private information that the model has never seen, and you split it up into chunks because vectors can only be on a certain size thing. So you split it up into chunks that are the appropriate size, and then you create a vector for each one of the chunks. Okay, you put all your vectors in your vector database, and now when a user comes along and asks you a question, like for example, what's the fee for a basic checking account? Okay, you turn that into a vector. The question, you turn the question into a vector. So you get a vector that represents the semantic meaning of, fee for a basic checking account. Then you do a vector search, which will find all of the vectors in your database that are close in meaning semantically to fee for a basic checking account, right? And typically you will take the top 3 or 5 or whatever, like you'll find the closest ones. And very often you will do something that we call re-ranking, which is to check that they really are close. Because if you search for something close to that dog, and you came up with like the tennis ball and the watermelon and whatever, they may very well have been the closest, right? But they're a very long way away, so they're not relevant. You want to throw them out. There's no point, using those. So re-ranking is where you like actually check that the answer that you got, how close was it, right? Just because the closest doesn't mean it's good. Yeah.
So if we have Oracle installed
Yep.
on a server, is there a way that we can use this internally? That we
Yep.
can? Are there tools? Will you go into that? You don't have to go into it now, but like a
Yep.
list of things.
Yep. You can implement all of this in the database, including running models in the database and all that if you want to, or you can connect it to an external.
And for developers, is available for free the way Oracle.
Yep.
Okay.
Yes. And all of this is available in the free version of Oracle for developers as well. Yeah. I will go into that some more later on too. Yeah. Okay. So we do the vector search, we find the things, we do the re-ranking to make sure that they're truly close. And then what you do is you retrieve the chunks that match those vectors, and you add to the question that you send to the LLM, which is going to do the reasoning. So you say like, how much is the basic checking account? By the way, here's the 3 most relevant documents in our corporate data set. But what's the answer? And the LLM will read them and do the reasoning and come back with an answer. Okay, so that's what RAG is all about. Creating an embedding, a vector embedding, is relatively inexpensive. Okay, you can do thousands of them for like a cent with someone like ChatGPT, for example. Or you can run the embedding model on your own hardware, where you can control the costs. But it's relatively inexpensive. You can create thousands, millions of these vectors for a relatively small investment. Okay, and it's pretty fast. So, and doing a vector search is pretty fast, especially if you have an index. Okay, so it's all pretty quick and easy. So compared to fine-tuning a model to make it learn about your data, this is like 3, 4, 5, 6 orders of magnitude cheaper. Okay, which is why it is so popular. Yep.
Sorry, it took a few seconds for this to click in. But you said you could use, for example,
Yep.
ChatGPT, as an example,
Yep.
to create these, I guess what you call them, intake vectors?
Embedding vectors.
Embedding vectors.
Yep.
I'd still have to expose my corpus, my private corpus, to
Right.
ChatGPT.
In that case, you would, yes.
In that case.
Yeah.
Okay.
Or you could run an embedding model on your own hardware.
I get
Yeah.
it. But
Yeah.
if I'm going to use a public model for the embedding vectors,
Yep.
I have to expose my
Yes.
IP to
Yep.
ChatGPT,
And a lot of
my
people
lawyers don't like that.
yeah, exactly.
Or, and this is something I do often because we're developer focused, I run Olama locally. I run Oracle 23 AI as a Docker container locally, and I can take content. I can keep it local. Then it hits my local to get my proprietary data, packages that up, sends that content off to the LLM that reformats it and kicks back the answer. So you could still keep your private data private. Well, mostly private, right? Just what you want to share.
Okay.
Yeah, exactly. So and that's a huge consideration. So we talk about self-hosting models, both the embedding models and the language models and diffusion models and whatever else. And as Doug said, there's things like Olama or VLLM or other ways that you can run them on your own machine in your own environment, so your data never has to leave your environment, right? And there's 2 huge reasons why people want to do that. Like you mentioned, lawyers, right? Obviously, nobody wants to send their private data, especially if you're in a regulated industry, because of privacy concerns, data sovereignty, or you just plain don't want to give OpenAI all your data so they can train their next model on it and get economic advantage from it.
Also going to pay me.
Right? And pay them for it. To pay them to steal from you. Yeah, nobody wants to do that. And the other one is, if you run your own models on your own GPUs, you know exactly how much it's going to cost, right? Because you know, I can run this GPU for $100 a day or whatever it is. Okay, so you know the cost up front. Whereas if you let people just go nuts talking to a public cloud service and you're paying per API call, then you have a variable cost. You don't really know how much it's going to cost you, right? I mean, you can keep track of it and stuff, but if somebody goes nuts and accidentally sends a million things to it, then you're going to have to pay for it. So,
And
yeah.
the more RAG you do too, if you're using a public language model, you're also stuffing more tokens, and each
Exactly.
call is now costing you more and more as the conversation goes.
Exactly. Yeah.
When you talk about the vectors and
Yep.
using the word here, is that the same as when the AI tech people talk about clusters?
Tell me more about
Sounds similar.
the clusters that they talk about.
To me, it sounds like what you're saying about vectors, so I can actually, maybe they are different.
Well, I mean, the vectors tend to be clustered, right?
That's
So,
what I thought maybe.
yeah, things that have a similar semantic meaning, their vectors will be close to each other. They'll form a cluster. Yeah.
Okay.
So I think probably yes. Yeah.
They're adjacent terms, so people
I think
get sloppy
so.
with them sometimes.
Yeah.
No, that came out early on. I mean, in the first year, the journal, it was part of the discussion. It doesn't matter.
Well, in
Actually,
machine learning, in machine learning in general, there's regression problems and there's classification problems. And classification problems are about finding clusters of things that are logically the same. Like, does this MRI image show cancer or not? Is a classification problem. So you get a cluster of things where it has certain little shapes or whatever, and like, yes, that's cancer, compared to another cluster of no, it's not. That's totally normal. So it could be, that could be, yeah. Okay, so RAG we talked about. So actually, I think I said this. This is how it works. So you take the question, you turn it into a vector, you send it to the vector database, you do a similarity search, you get back the closest vectors. Normally we re-rank to make sure that they're actually relevant, not just the closest ones by accident. Retrieve the chunks. Yeah, sorry.
You check to see if it's a person who has to say whether they're.
No, it's computer code.
Okay, so
Yep.
it is they're going by the distance and determining that in
Right.
this case that distance matters a lot more.
Yeah. Like, say if you did a query like what's the nearest Five Guys burgers and fries to Boston, and it said it's in California, like you would say, well, that's not a particularly useful, like, I don't care. I'm not going to drive to California to get a hamburger, right? So maybe it's the closest, but I don't care, So you can tell by the distance. Like if the closest one happens to be a very large distance away, then it's actually not close.
No, I understood all that
Yeah.
completely.
Yeah.
It depends on whether it matters. So
Yeah.
you certainly chose a case where it matters a lot, and there are lots of cases where it won't matter very much.
Exactly.
So
It totally depends on the data. You're right, for sure. Yeah.
So I'm trying to picture the math knowing that for sure and assuming that's where a lot
It's-
of human review.
It's a tweakable, right? Like when you're building your solution, you're going to set a threshold.
But you really have to know all of your data so well
Yes.
to get that correct.
Absolutely. Yeah, you need like a data scientist who knows about, all the statistical measures and moments and things and understands distributions and stuff.
Put in the embedding data,
Yeah.
how much you chunked versus overlapped, or
Yes,
you gotta
exactly.
understand the data that went in, because
Yeah.
otherwise it's garbage and garbage.
Yeah. And you're right. And I have that. I'm going to come to that chunking thing later. But it's interesting. Like if you have if you choose a large chunk size versus a small chunk size, you're going to get completely different outcomes, right? And depending on the type of questions that you're asking, if the question is something that requires a lot of context, like say you're saying, how do I write, a singleton class or something? If your chunk size is so small that it can't possibly contain all of the code for that, then you're never going to get the right answer because it won't be in a single chunk, right? So, yeah. Anyway, we'll power on.
Are you getting into that, the chunking?
Yeah, I have that later.
That is a key issue with
All right, I'm going to
That's
power
just
through.
generic.
No, there is no.
Okay.
I've been using some graphing algorithms to help with that.
Yeah. So we talked about this. You get the content back. You send it to the LLM. It makes it. So the LLM is using its general knowledge plus your data to come up with an answer to the question. Okay. So this is a little thing. So this is kind of the pipeline. So you start with your data, what we call the corpus. You go through these document loader things, which are things that know how to read documents, that understand what is a heading, what is a page, what's a footer, what's a table, blah, blah, all that kind of stuff, list, all that kind of stuff. Then you transform them, you do the splitting. Typically, there's some other stuff that goes on too, like, we get rid of what I call stop words and punctuation and stuff that doesn't really make any difference. Then you feed it into the embedding model. It creates the vectors, you put them in your vector database, then you can
Splitting, what you said, chunking then?
Yep.
Okay, splitting and chunking here. Is not-
Yep, chunking, splitting, same thing. Yep. Similarity search, and then you have the LLM. So you do the search, you retrieve the chunks, give it to the LLM, it does the reasoning and so on. So that's like the full RAG kind of life cycle. And I will say one thing, all of these things about 5-minute chatbot and blah, 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 this part here, there is no way you're doing this in 5 minutes if you have more than like a couple of kilobytes of text. There is no way that's happening in 5 minutes. It's taken you days, to do that kind of stuff with any reasonable amount of data, just because of how fast GPUs and these models and things operate. I saw, yeah.
A couple of years ago now, with ChatGPT, when they brought out RAG, I
Yep.
pointed it at a set of public documents that were several hundred pages.
Yep.
And it totally failed.
Yeah, exactly. Because it's not that simple. Like, you've actually got to know a little bit more. Like, whenever any new technology comes out, they go, oh, this is great, it's going to solve everything and blah, 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 and it's so easy. And we all know that's not true.
In this pipeline, where's the importance of needing like a special processor, like you know what I mean,
Like a document.
like an NVIDIA chip or something.
The embedding models are written to run. These do lots and lots of matrix manipulations and calculations and stuff. So you can run them on CPUs, but they'll be slow. When you're actually running your chatbot or assistant or whatever, and you're only creating embeddings for the questions that the users ask, you can run that on a CPU, because you wouldn't, for one question, you're not going to notice the difference.
So if you're doing a lot of matrix math, and
Yeah.
that's why you use a video chip, because
Yeah.
it was doing transformations.
Yeah.
Using matrix math or something.
Exactly. Yeah. So NVIDIA call them GPUs, graphical processing units. Really, they're just very good at floating point arithmetic and matrix manipulations and all that kind of linear algebra and that kind of stuff. So other vendors call them different things, like tensor processors and neural chips, but they're all the same thing.
Right.
Yeah.
And if you want to play like the M3, the MacBook, the M3s, they're GPUs. So that's why it works pretty well. Like when I'm playing on my MacBook with those things I talked about before. Because you have a GPU right there.
Yeah, but a smallish.
Yeah,
GPU.
smallish, but it's there.
And there's different kinds of GPUs that are good at different tasks too. Like, some of them are really good at training models, which is heaps and heaps of matrix math, right? Some of them are good for inferencing, which is like the chat. Some are good for high performance computing and scientific calculations. So, like NVIDIA have the different series, like the A and the V and the H and whatever. They have different strengths, so they're good for different things. Yeah.
You just need some library that recognizes and uses a GPU over a CPU.
Right. Exactly. And these models, the libraries that you use to run these, like Olama or Hugging Face or things, they understand. They can detect the GPUs.
Yeah,
and stuff.
I didn't have to do
If you
anything.
had two, like Kubernetes or something, you have a multi-architecture cluster, and you have tolerations or something to put workloads here.
You can have some worker nodes that have GPUs in them, and like put a label on them or something, so that you can put a pod spec that says, schedule this pod on a GPU node or whatever. Yep. Okie doke. Okay, so chunking. I'm just going to keep talking until you throw me out, okay?
This is
8:30 to grab comments.
No problem. Okay. So chunking is a lot more difficult than you would think. So consider this. This is a page out of an Oracle manual, which is some of the most difficult to read information ever created in the history of the world. Anyway, but if you look at this, say your chunking strategy is like pick the next 500 words, right? So the red box is your chunk, right? But if you look at it, what do you got here? You've got some code, you've got headings, you've got half a list, you've got page number, a footer. This is not in the chunk, but here's an image. A lot of these text models don't understand images, right? So this is a big mess, big mess. If you go take that chunk and use that to create a vector, you're just going to have garbage, right? It's going to be meaningless. You search for something that's similar to that, you're going to find garbage. It's not going to work at all, like you said.
Right.
Garbage, okay? So
So the chunking algorithm's got to understand what the headers are and the lists are.
Exactly.
And auto chunk them.
Exactly.
Right? The list elements together.
Yeah.
You
So
hope
typically
that.
you have what we call a document reader that will go through and understand things like headings and things. So it'll know like you don't need the footer, or whatever. Like if it finds a list and so on, it can maintain the structure of the document. So it'll know that this is part of chapter 3, which is in section 2, and blah 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 blah, all that kind of stuff. And then if those are still too big, then you split them up into smaller pieces and you chunk those and create the vectors from those. Okay, so some of the newer models, the multimodal models, also understand things like images. So if you get an image here, it can actually look at this image and kind of understand what is the semantic meaning of this. Like, is this some kind of composition, or like what is this talking about?
Is it a dog?
Yeah, is it a dog? Is it a big dog? Exactly. So chunking is super important, and like if you get this wrong, then everything else is going to be garbage, right? The whole way, like it doesn't matter. The whole way down, everything's going to be nonsense. So structured trunking, like I talked about, this is where you use a reader that understands the headings and topics and stuff like that. So it lets you do things like avoid including headers and footers and so on. And there's literally, again, hundreds of different types of document readers that understand different kinds of documents and formats and things and help you to create, to break them down in a meaningful way. So there's another concept called context. So context is important. So consider this sentence. Jones made a deep cut in her leg with a very sharp knife. Okay, what's going on in this sentence? What does it mean? Who's Jones? Who's her? Is Jones her, or is that another person? Like, what's happening here? Okay, so you could ask, this is an example of asking, I think this was ChatGPT, it might have been Llama, I can't remember. What's going on? And see, it says, blah, 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 she intentionally injured herself with a sharp knife, etc. So now let's look at it. Imagine we have some context here. The fight was uneven. Jones had a knife. She hit Jones hard on the side of the head with a roundhouse kick. Jones made a deep cut in her leg with a very sharp knife. She fell to the ground in severe pain, bleeding heavily. She soon lost consciousness. So now what's going on? Who's Jones and who's she? Like you can tell there's two people, right? And you can tell this is an altercation or a fight or something. And interestingly, the model still said she cut her own leg, which is probably not how I would have. I mean, you can't tell, obviously, right? Like I heard you talking before about languages and stuff. Like you can't really tell from the language, from the words in English, if she cut her own leg or the other woman or whatever. But I'm pretty sure she hit the other woman, not herself. Here's another example. She lay on the operating table unconscious. Jones made a deep cut in her leg with a very sharp knife. Blah, 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 blah. So what's going on now? Jones is a surgeon who's cutting the person to help them, right? To remove a bullet or whatever, I don't know. Okay, so you can see how the context is super important here, right? Like you've got three completely different meanings because you have that extra context. So there's a very interesting new technique called sentence window retrieval, which is where you use a very small piece, like a sentence, because in English, a sentence is meant to represent a single complete thought, right? And you create the vector from the sentence. So when you create the vector, you're trying to capture the semantic meaning, right? So if you do that on the sentence, the idea is that you're getting a very specific meanings so that when you do a similarity search, you're going to find things that truly are similar to that one sentence. But then when you give the result to the LLM, you don't just give it the sentence, you give it the whole context, like the whole paragraph or whatever that was around that sentence, so that the LLM has much more meaningful context to understand what's happening. And so this is one example. There's like hundreds of these techniques. There's new ones coming out literally every week. Like people are publishing papers with all kinds of techniques of how to improve the efficiency of models and all that kind of stuff. So this is one that I find particularly interesting, sentence window retrieval. And there's a bunch of others, right? I'll
So
talk
here,
quickly.
Can I just talk quickly about the graph using RDF graphs?
Yeah,
As a
do
way
that.
that, like, when you look at like a 10K document, like a financial document, they're huge, right? And there's parts maybe on page 3 that reference some appendix note in page 17 and the whole bit. And apparently there's this thing called RDF graphs that capture semantic meaning. So what we did, I have a thing on GitHub called RDF Chunker, but what we did is we took like a document, like I think it was our vector indexing document, right, which had like sections, and then it would have like code over here, and then it would have an appendix over here. But you could see that like some of these techniques wouldn't really capture everything and make it correlated, right? So you could use this graphing mechanism to sort of define. This is like a manual procedure right now. You have to like know the document and define the relationships. So then you can embed the relationships that these RDF graphs have discovered as you're generating the vectors. So now you're making vectors that are more closely related in clusters based on these relationships that you've done through these RDF graphs. So, and they tend to give better information.
Is that with tags or labels or text?
Gotta remember, I was doing it a while ago, but you have to like understand your document, and then you give it like this framework that talks about this relates to this and this relates to this, and now take this information from my graph, combine it with the content, and use the vectors to create your clusters that way.
So you do see like there's a config file that matches.
Oh yeah. Well, back to where it started. Right. So, but that has proven useful for larger documents.
But you mentioned just in there something about like it's a very manual process right now.
For me, I'm not an expert, but yes. Yeah.
But is that like setting up the graph and using it?
Yeah,
or
like setting up the graph.
Every single
like
document that I'm trying to embed, I still have to manually, tag and describe whatever. Or is it? I mean, like how?
Maybe you could generate a template over time, but I haven't gotten there yet, right? Like right now, I'm just trying to really understand these graphs and how you build it. But I've seen it improve the results dramatically when you take that information with the content and turn that into your vector. You're gonna more likely cluster related stuff as you perceive it to be,
and
right?
This clustering, that's part of this
chunking.
Window.
Yeah,
it's part of the chunking.
It's part of creating the vector chunks that are closely related.
Yeah, so the embedding model will naturally create clusters.
But you said it improves the results, but that's based on
It's on the retrieval side.
human judgment, right?
Yes, and it's based on because the document, sometimes the information is spread out over the document. When you're doing some of these chunking techniques, that it doesn't know, right? It just doesn't know that maybe this bit of example code in the example section was related to this topic on page 3 that was discussing conceptually what it did, right?
And then what happens when they publish a V2 of that paper where they only change 3 words in the paragraph?
Yeah. That's a big problem, actually. Getting new data in and creating new vectors, and knowing when to update the indexes and stuff. That is a big problem too. Okay, so let me talk a little bit about context window. And when I first wrote this, it was like maybe a year and a half ago. This was a big deal. Now it's kind of irrelevant. But let me just talk about it just for general knowledge. So models have a concept called the context window. This is the amount of data that they can see, that you can send to the model and get back from the model. Like if you're calling a function, if any of you ever wrote COBOL, like me, you got to tell it, you're going to get 20 bytes. You can send me back 20 bytes or whatever, it's like that. So the context window is how much data you can send to the model and it can send back to you. And there's a bunch of stuff in there. So the question that you ask it is in here. Typically, there's also something called system instructions, which you don't typically see, but like when you use GPT or something, there's actually instructions in there that say to the model, like, you're a helpful assistant and you want to be honest and truthful and blah, 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 all this stuff, right? There is also, if you're using RAG, the actual content has to go into here, right, that you're going to send to the model. If you're using memory, so that so that it remembers like what you asked the previous question and so on, you've got to send a summary of the conversation up to that point, or the whole conversation, or whatever, backwards and forwards every time. If you're using agents, typically they have a response area, and then the answer's got to fit in here as well, right, that it sends back to you. So, a year and a half ago, these were small, like these might have been like 4K, for example. These days, modern models, which is crazy to stand here and say this because it's like been a year, but models now have 100,000, 200,000 megabyte context windows. They're huge. These days, not really a big deal. Often I get a question like, well, if they're so big, why don't you just send all your documents to it? Why do you need RAG? Just send all the stuff to it, which is interesting. But like, you've got to also think like, how is it going to work out? Is it got to read all of that and figure out which things are relevant and appropriate and related to each other and all that kind of stuff? Like, that's a lot of work, right? Still, RAG and vectors vector searching and stuff is still a much more efficient way to do that than asking a model to do it on the fly every time, and cheaper.
I guess you could do that if you wanted to keep that data private.
Well, they're going to be private anyway. If the model is self-hosted, right? Yeah. If you're not going to a public model, if it's your own, if you're running the model,
I've been experimenting with Claude Code a lot lately, and you can see it. Like, even though the context windows are huge, as you have a long conversation, say you're having a conversation, it's gone a couple hours, you can see all of a sudden it'll stop. It'll go like, I'm compressing this right now, and
then
it'll
it'll
pause.
send it to a summarization to summarize its own history so that it can send it back and trim its context.
Exactly. Yeah, and there are things that do that are called like conversation summarizers and things, and there's all different ones of those too that do different ways and so on. So that's another whole, thing in and of itself. So the prompt, I mentioned the prompt. Prompts are what is given to the model. So this is an example, I think from memory, this is a Llama formatted. Yeah, this is a Llama 3 prompt. So you see they have these special tags that tell it, here's the system prompt, here's the user question, here's the context, blah, blah, blah. And every model has a different way that they expect this thing to look, right? They're all different. So you can't, if you want to try different models with the same thing, then you've got to go and figure out, well, what's the format that it wants, all that kind of stuff. So that's a lot of work. There was a whole thing about prompt engineering. Like, you could go and do a course, a prompt engineer to write a really good prompt to make the model do the right thing. And they make a big difference. It's true. Like, how you ask the question has a very strong impact on the answer, right?
Yes. My 12-year-old.
Yeah,
different answer.
Exactly.
I've found, like, when I code with it, I found that, like, LLMs, they want to be very helpful, right?
Yeah.
They want to solve world hunger, right? And as I'm asking it to code stuff, I'm like, I don't want all that. So I have a very generic prompt that says, just give me the simplest answer. We'll start from there, and then we'll move on, right?
So if you were going to have the best prompt, then you would want to know what all the vector parameters are, right? Like, I want to know that it's creating vectors on dog and large.
No, you don't need to know that. It's the search is going to find the most similar things. So you don't need to know how it works.
It's
Yeah,
like
but-
the temperature thing.
But if
Well,
it's-
there's a bunch of them.
Yeah, but
Yeah.
if your vectors are based on axes and
Yep.
lots of axes,
Yep.
if you created a prompt that used all the axes, it
Yeah.
would be very specific.
You don't give the vectors. So first you do the vector search to find the things that are similar, and then you retrieve the actual content, like the chunks that match that. It's the chunks, the actual content that you give to the LLM, not the vectors.
Yeah,
So-
but I'm saying if you created a prompt
Yep.
that used the vectors and you knew what they were,
Yeah.
that would be the best match, right?
It's I would say it's the likelihood of you knowing what they are is so close to zero as to be unmeasurable with any modern model.
So if I knew the axes were large and dog,
Yeah.
right?
Yeah.
And I would say, you know, I'm looking for a
For a lot.
medium-sized dog.
Yeah.
You know, 5 pounds or something like that, right? Average
Yeah.
weight 5 pounds. And because it's structured, it's vectored that way, it can give me the best answer
Yeah.
according to that question, right?
Yeah.
That's not how it's actually
But
structured.
Right.
the prompt is more like constraints, I guess. A prompt is more like constraints in that, like I could say, like I've been using a lot to code lately, and we have check style. I don't know if people use check style for how our code gets in, but I was tired of it generating me code that I would have to fix up all the time. So I was like, here's my check style.xml. Make sure any code you generate for me follows this, right? And that's like an example of how you would use prompt engineering.
Yeah. So in real life, like today, the models have the embedding models create vectors with thousands or tens of thousands of dimensions, and so the ability for you to know what the dimensions represent is almost non-existent.
Yeah.
Right? It's very like it's not like large and dog. It's you don't really know, and it's not even something that you could necessarily put a name to or a concept, right? It's just because of the way the model has been trained and the weights and whatever through the neural network, like it's really, that's what's creating the vectors. Like you feed the embedding models are neural networks as well. You're feeding the input in, it's doing all these calculations through the hidden layers that were trained on a whole bunch of data and coming up with a vector and the output layer. So it's kind of meaningless to you or to anyone. Like even the model doesn't even know. Like no one knows what it means. We know it works, and we kind of know how the math works, but nobody really knows like what it means.
And that's the magic.
That's the magic.
It makes it almost impossible to debug, right?
Yes, it makes it impossible to debug. Yeah,
But
It
I still
does.
think it's a good idea.
It does make it hard to debug.
Yeah.
Right?
So a super hot topic at the moment is what we call explainability of models, which is very important in highly regulated industries, right? So people want to know, like if someone come and said to the model, like, which checking account should I get? I want to save up for my college, blah, 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 whatever, or which savings account should I get for this? And it's going to give you an answer. So regulators expect you to keep the question and the chain of thought and the data and all the stuff, like how did you come up with the answer that you gave? Why? What was your reasoning, etc. So you can do that. LLMs can do that. There's ways for you to have observability and explainability and traceability so that you can record how it came up with the decision and stuff like that. I wasn't really going to touch on that, but that is for real. That is a thing, a very important thing in a lot of industries. Yeah. Okay. What else do I want to say about prompt engineering? I think we're good. Okay, parameters. Models have parameters. I'm not going for time here. So models can have lots of parameters. And actually, these are called hyperparameters, technically. When they talk about model parameters, like when you hear like ChatGPT has 20 billion parameters, for example, in the neural network, every weight and bias is a parameter. So if you add them all up and multiply, every node is connected to every node in the next layer and so on, you multiply it all out, that's where the 20 billion comes from. So when they say this is a 20 billion parameter model, it means there are 20 billion weights and biases when you add them all up. Okay, so these are technically hyperparameters. So these are parameters that affect how the model behaves after the model training has been completed. And there's a lot of them. So some of the common ones are here. So temperature is one. Temperature controls how creative the model is. So 1 is meant to be kind of normal. If you make it closer to 0, then it's going to become more deterministic, more repeatable, right? So if you ask it the same question multiple times, you're much more likely to get the same or a very similar answer if the temperature is very low. If you make the temperature high, meaning greater than 1, then it becomes free to be a lot more creative, and you'll see it will give a much more creative and interesting answer. And if the answer is longer than maybe a few hundred tokens, you'll notice that it just goes completely batshit crazy and starts spewing out all kinds of garbage. Okay, which is
So you
if you
evolutionary
exactly, yeah, like it won't even bother with text. It'll just be spewing out characters of nonsense. If you haven't done it, go and try it out on ChatGPT or something. Set the temperature to 2 and ask it a simple question. It's hilarious.
I mean, you may or may not know it, whatever. But
Yep.
I'm just curious, like, so if I'm a generic whatever user and I'm typing some stuff into Google
Yep.
and it's giving me an AI summary or
Yep.
whatever, I have no control over
No.
any of these.
Those are all cached. They're not. It's not doing that live. They're looking at the most commonly used queries across all of the search farm, and they're picking the top queries, the most important queries, and they're generating AI summaries offline and caching them. So when you get that AI thing at the beginning, that's cached. That's not being done in real time.
Got it.
Yeah. But yeah, you have no control.
But even if it's like there's no hope.
Even
for
so,
me to
you have
say,
no control.
You know, I have like
Yeah.
I want a low temperature answer.
No.
No, and you would it's set based on the application you were building and the context
Right.
you're building it for, the industry you're building it for.
Yeah.
Go and set these.
Yeah.
But these are also this is for the model all the time.
Yes.
Not for a particular query. It's not
No, per query. Per query. You can
It's
change
per
it.
query
Yeah.
temperature.
Yep.
Okay.
Yep. Per query. So you can change it all the time.
Okay.
And there's a bunch of others. Maximum tokens tells it how long the answer can be. Top P means probability, tells it how many candidates to consider when it's coming up with the next word. There are penalties for different things like frequency and so on. So for example, if you set a high frequency penalty, it won't use the same word over and over again in response. It'll choose different words. You know, it won't say the large dog. You know, Saint
It's
Bernard
large.
dog is a dog that's quite large. it'll start saying large and big and massive, and it'll pick different words. And there's a bunch of these, right? So you can see all of these can be tuned, right? You can pick the different model. You can mess with the prompt. You can tune all of these parameters. You can see this is starting to add up, right? We're multiplying all of these things out, which is why it's so difficult to create a good.
Takes more than 5 minutes.
Yeah, it takes more than 5 minutes. Okay, so now I'm gonna change gear a little and talk about our tool, our open source tool. It's called AI Optimizer and Toolkit. This is
Did you already say we're gonna get a copy of these slides? Is that
Yes.
Okay.
Yeah. And the video and everything will
I'll
be.
link them to the video.
Yep.
too.
Yes.
So this is an open source tool that you can use to play with any model, any kind of embedding model, any inferencing model with your own data, and optimize for whatever you're trying to do, whatever outcome you're trying to get to. So you might want to optimize for cost, lowest cost, or the best performance, or the most accurate model answers, or whatever. Like there's different things you might want to target. It has a bunch of tools, things like document readers, splitting, chunking, creating vector embeddings, creating vector indexes, tuning them, doing semantic searches, securing your vector store and filtering access to it, generating Q&A data sets, which I'll talk about in a minute, generating code, using MCP servers, all that kind of stuff. So a lot of the stuff we've already talked about. So the way this works, it's a no-code tool. You go into your browser, and you can pick, what do you want to do? You want to, talk to a model. You want to do your splitting and embedding. You want to fiddle with the prompts. You want to do some testing, all that kind of stuff. Oh, thank you. Thanks very much. I got salsa. Do you want one? I got two. There you go. Thanks. You can tune all the parameters for the model so that you can make it behave differently. And you can also enable retrieval augmented generation. So once you've done your splitting and embedding and you have a vector store with all your vectors and chunks and stuff, you can turn that on. And then it has parameters too. So we talked before, there's different types of searches, like the cosine distance, Euclidean squared, Manhattan dot product, blah, 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 all that stuff. You can pick which one you want to use. For text, cosine is the only one that's any good. Okay, cosine. For text, cosine is what you want. Yeah. Like it's been well established academically that cosine similarity works best for text. But for other things, like for images and stuff, like Euclidean distance and things are much more useful. You can use different embedding models. When you do a search, there's a parameter called the top K, which is how many results. Like, do you want the 4 nearest things, or the 3, or the 10, or whatever? Like, how many do you want to consider? And that has an impact as well on the size of the chunks and the size of the context window, obviously, because they have to fit in the context window. So there's no point getting back 10 megabyte chunks if they won't fit in your context window, for example. Chunk overlap was mentioned earlier. So when you do chunking, typically you overlap them. So instead of like making them like this, you sort of overlap a little bit so that your search might get 2 that are sort of close to each other, and so on. That's showing you like creating the embeddings and stuff. You can play with the prompts. And then another really interesting feature this has is something called evaluation. So imagine how you would use this tool, or if you didn't have this tool, you'd be writing your own code for every one of these permutations and combinations, right? So you have your data, you've created your vectors. Maybe you do it several different ways with different document readers, one that understands structure, one that doesn't, different chunk sizes, different overlaps. Maybe you experiment with different similarity search algorithms. Maybe you fiddle with the temperature or the top P or all that kind of like, so you can imagine you're going to try lots of different combinations to try and figure out what's the most reliable and effective for whatever it is you're trying to do. Like,
you just put all that data into another model?
Yeah, you could. People do. It's a manual process, right? You've got to go and try all these different combinations. Oh, that's a little better, and then you keep going and whatever, and eventually you're going to find the one that works the best, right? So then the question is, how do you compare them, right? So you've got to remember, what did you set it to and all that kind of stuff. So in here, when you do this, we save all of your choices and everything. Typically, you create what we call a Q&A, question and answer data set, which you use to evaluate the performance of a model and a set of parameters and so on, okay? So a Q&A data set can either be created by human experts, which is, again, very expensive, like we talked about before, but much better because they actually know what they're talking about. Or you can have another LLM create it for you. So you might take a second LLM, and it's very important that it's a different LLM from a different family of LLMs, right? So if you're going to use, no, but it's bias. It's because of bias. Like if you're going to use ChatGPT, yeah, it's the same. Exactly. Yeah, we don't want any AI incest. You got to edit that bit out, okay?
Otherwise, it'll be demonetized.
You can't say incest on YouTube. So you got to have
for over 18.
So you got to have a different model from a different family. So if you're going to use like a ChatGPT model, for example, to do your inferencing, you want to use a Llama model to create, or a Grok model or something else, right? So that they have different biases and probably being trained on different data, and they definitely have different weights and everything. So you can create the data set. So that's much cheaper, obviously, because the model is doing it, but it's not going to be quite as good, right? Because it wasn't a person who actually knew what they were talking about. It was a model, making it up. So you create this data set, and basically you have a question, you have the answer, like the human answer, the right answer, and then it has details about why that was the right answer and that sort of stuff. So if you said like, what kind of savings account should I use to save for my college thingy, blah, 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 or whatever, and the correct answer might say you should use one of those 529 savings accounts, and then it'll say, they should mention it's a tax deferred saving account or whatever. I don't know, like whatever, right? And then you have your data set, and the more questions in this data set, the better it's going to perform. So say you have 100 questions, these gold questions, and then you have like say 100 different sets of models and combinations and things that you want to test. You run it through, and you get a score for each one. And you're going to see, with this model and these parameter settings and this chunk size and using cosine search and blah, 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 it got 73% of them correct. And with this other one, it got 86% correct and so on. Okay. So this evaluation thing is a tool to basically automate that process for you. So it'll run through all the different settings, collect all the answers, use another LLM to score the answers. And again,
it's like now a third LLM.
A third LLM, ideally.
And again,
yes.
Non-incestual.
Non-incestuous. Exactly, a third one with different biases to score. So you may hear the term LLM as a judge. They call this as well. Okay, so it's going to score how the first guy did, right? And it'll come back, and you'll see the output will say like, it didn't mention that it's tax deferred, so it's only half correct or stuff like that. And so basically, this is what you do. So you iterate, you do this, and eventually you get to theoretically your best possible optimum solution for your exact data and use case and so on. Okay, so this is what this tool is for. What else do I want to say here? I can also.
Just backing up. So that's,
Yep.
like, you have your main LLM that you're sort of evaluating.
Yep.
That's one. But you're using two auxiliaries
Mm-hmm.
in this style
Yep.
to do the evaluation.
Yep.
And then you've got, before we also talked about yet another one for doing embedding.
Yep. That's an embedding model.
An embedding model.
Yep.
And is it like now
now you may choose different embedding. Like part of this may be exactly the same model configuration and parameters and everything, but with different embedding models.
With its own set of parameters.
Right. So you might say, well, if I use like the Nomic model, for example, compared to the one from OpenAI, compared to the one from Meta, compared to which embedding model gives me the best semantic search results. Right.
So that's all part of the scenario that's being evaluated.
Exactly. Yeah.
Okay.
What's that website that has like the collection
Hugging Face.
What?
Hugging Face?
No, what's Hugging Face? There's a website that just lists embedding models, just like pages
Hugging
and
Face.
pages of them.
Hugging Face is like a marketplace for
Yeah.
models and data sets, like Q&A data sets. So there's standard ones, like you can get a data set of like, I don't know, there's one called MNIST that has people writing numbers, right? It's got thousands of handwritten numbers that you can use to train a model to recognize handwriting, right? For example, there's thousands, tens of thousands of these data sets and models and things.
Going back to the evaluation, so you have,
Yep.
you have one model with one set of data, and then use a different model with the same data, I
Yep.
guess, that checks the results of the first guy.
Yes.
What if the first guy's results were better than the evaluator?
Then not ideal, right?
Well, so you're getting an evaluation.
Well, you're
It's
going to
not
have
showing
the gold standard, the human
Well, so the
created
the
answers.
system you're testing
Right.
was better than the evaluator. So
Yep.
you get an evaluation score which doesn't accurately.
So the
reflect-
evaluator.
The judge is comparing the
Yeah.
model results against a vetted standard answer.
Correct. So it's just
So instead of
reasoning.
a
It's
human
not
being
answering
saying,
the
"Oh,
question.
Here's
not
the
answering
model.
the
Here my
question.
chat
Yeah.
told me this, and it should have said that." And a human being didn't know. We're going to use another model to do that comparison, but it's still comparing against the gold standard answer.
Exactly. So it's like if I gave you,
presumably by humans.
yes.
At this point, I mean,
Yeah.
later.
Yeah. So if I gave you like I don't know, I give you a question like which side of the road should you drive on? The answer is you drive on the right-hand side of the road.
If you're in the
If you're in America,
US.
or whatever, right? Whatever. And we would list like, blah, 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 blah. And then you feed it through the model and it's going to come up with an answer. So the third model, the judge, is comparing those two. It said, well, humans said you got to drive on the right because you're in America and blah, blah, blah. And the model said you drive wherever you like. Well, that's wrong, right? Because they don't match. So it's not answering the question. It's just comparing the two answers to see if they're correct, to see if that answer matches that answer.
Well, I mean, so what if this first model is using American data?
Yeah.
And the evaluator is using British data.
Which comparing the answers. It's not answering the question. So it's not like you have two models competing with each other to get the best answer. The third model is just comparing the correct answer to the answer that you gave, basically.
Narrower scope.
Yeah, that's a much easier thing for an LLM to do than to actually answer the question in the first place. Yeah. What else do I want to say here?
It's like doing a scorecard against
Yeah.
against-
It's like a rubric.
Then you think about it too, like as your system is in production and it goes and goes and goes, if you're not recording questions and answers,
Mhm.
make it then change. You're still doing all this piloting on the
Yeah.
back end for your next version. Well, how do you know if it got better or worse if you don't have a history of what it was doing in the first place?
Yeah.
So that's what I was coming back to. Like, you said, what was it? Narrow the temperature.
Yep.
And you can create a test suite
Mm-hmm.
that always produces the same result, right?
not guaranteed, but it's
If you
much more
want the
likely
same
to.
result, why are you using an LLM in the first place?
But no,
Right.
no,
No, for testing.
No, for testing.
So
You want the same you want the same result for the same question in testing.
Yeah, so that's why we have this LLM as a judge, because it's not like a unit test where 2 plus 2 has got to be 4, right? So the answer it gives, like if it says you should drive on the right because you're in America or whatever, or it could say in America we drive on the right. Those are both the same thing, right? The meaning of those is both the same, but the sentences is different. So it's not like a test like we would think of as a developer. It's more like a it's another semantic similarity. Yeah.
Which involves yet another vector.
Right.
Whole caboodle. Every time.
Or matrix math, more matrix math.
We're living in the matrix.
Yeah. So the other thing this toolkit does that is interesting is once you've gone through all of those cycles and iterations and stuff, it can just spit out the source code for you. Okay, so it'd go, okay, you picked the best one was happened to be whatever, llama 4 with temperature 0.87 and top K equals 4 and whatever, this embedding model and blah, 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 whatever. And it will just spit out the source code for you in Java, Spring AI, LangChain, or Python, or LangChain for J. Okay, so then you can take the source code that works with your model and whatever and has all your settings and check it into your source code system and do whatever you like. So this is really a tool for developers to do like rapid iteration and testing. Okay. What else do I want to say here? I haven't got my MCP slides. Okay, so a couple of things. Another thing I want to talk about is agents or tools or function calling. They all kind of mean the same thing. Different people call it different things. So RAG that we talked about, retrieval augmented generation, is about giving a model access to knowledge, like data. Tools or agents is about giving model access to functionality or capabilities. Like you might want to say, yeah, here's a tool that you can use to launch a nuclear missile. Don't do that, okay? If you're watching at home, don't do that. We don't want that. But you might want to let it send an email or do some math or run your policy quote tool to get a price or right. Stay away. We actually live in the same town. We have a nuclear missile silo in our town. It's not not used anymore.
Yeah.
It's been decommissioned. And now it's an artist's commune. Yeah, but the whole
But
it's
we
still
do
there.
see weird things
Yeah.
going on.
It's an artist commune. Yeah, but the hole is still there. There's no missiles in it anymore. Yeah, they're pretty big. Okay, so yeah, tools. So the way this works is you define the tools and you say to the model, here are your tools. You can, here are your tools that do. This one will send you an email. This one will give you an auto insurance quote. This one will do whatever. Okay, and then you'll come along with the user will come with a question like, I don't know, how much does it cost for a check account? And it'll go, well, for that, I can just use a RAG, right? That's just knowledge. It'll go and look it up. Oh, it's $25 as long as you keep $5,000 minimum balance, blah, 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 whatever. Okay. If they say, did the check that I sent to Doug clear yet? And it's like, oh, now I need a tool, right? Because that's not knowledge. So I need to go and check in the ledger to see if the check is still pending or if he's cashed it or whatever. I don't know. Okay. So that's an example where it would use a tool. So basically you give the LLM a list of these tools. Each tool describes what it can do. And the LLM decides for itself if it wants to use a tool, which one, which group of tools it can use, whatever it likes. So it'll go and do these. If you've used something like Perplexity or Claude, they're very highly agentic, we say, or they use a lot of tools. So you'll notice if you ask them a question, you'll see it'll say like, oh, I'm searching the web, or I'm searching academic, research paper archive or whatever. All these little things will pop up. You'll see it using tools to get information or do things before it actually gives you the answer to the question. So that's what that is all about. There's a protocol that was created by Anthropic called MCP. Yep, sorry.
If it's going and searching the web.
Yep.
Is it bringing the documents back as chunks which
Yep.
then get vectorized?
Not necessarily, but it could be, yeah. it's probably at that point more likely to be just feeding them straight into the LLM through the context window.
Oh, I see. Okay.
Yeah, but it could be. I don't know. I don't know what. I mean, it could do anything,
So
right?
I have a bunch of documents that I put into a vector database and I do a similarity match where I get out
Yep.
chunks.
Yeah.
Feed into the LLM.
Yep.
Thanks.
Exactly.
But it could also queue those up for later embedding too.
Yes.
Say, oh, by the way, here's are things that I needed to fetch ad hocly.
Yeah.
Let me just put them into the model in the first
Yeah.
place.
Or if it
And
does
they-
a live web search, it pushes HTML tags, but then you can't do semantic similarity on the fly either.
It kind of can, but it's different. There's different techniques to do it through the matrix calculus stuff.
Anyway.
Yeah. And they keep everything you ask it, right? Like they're not throwing that away. They're keeping all that to train later models on, which you would also do. Like when you're testing your own models, right? You would keep all of that history, all the questions, all the answers, and everything, so that you can use that later to train or
People
to.
really are asking.
Yeah, exactly. Yeah. So I want to talk about MCP. How am I going for time?
Yeah.
Not good.
No.
Okay.
I just want to.
You want to say something?
To go through the MCP stuff, I would just like to poll people about the one tool we were talking about for Oracle to see if they would find that interesting as a tool where it could discern communities within a database for microservice API generation. But yeah.
Okay. So let me talk about Anthropic, who are one of the small number of companies who train these models. There's like 20 companies that actually train the models and spend all the millions and tens of hundreds of millions of dollars to train models. They come up with a protocol called Model Context Protocol, or MCP, which you might have heard MCP getting bandied around. I'm sure all the CIOs are reading about MCP on their magazines on the airplane. So this is a protocol to allow models to talk to tools, essentially, and other stuff as well. But at the core, that's what it does. A standard protocol to let models have tools that they can access. And there's hundreds of the people who have written these MCP tools for all kinds of stuff, right? There's ones that can send email. There's ones that can make a calendar invite. There's one that can book you a hotel. There's like thousands of these things. We do have one as well, which lets you access the database. Okay, so it lets you do really interesting things. So if you give a model this tool, I did an experiment. I gave a model a tool and I said, okay, what can we do with this? I have a YouTube video. If you're interested, you can go watch. It's like, well, I want to create like a application for shipping products to customers or something like that. Like, help me figure out what tables I should have and so on. And I went through a whole thing like, oh, what kind of indexes, blah, blah, blah. Can you create me some sample data so I can test it? All this kind of stuff. And then I got to a point where I was like, okay, so this is great. So now if you look at all my data that I have, like my orders that I've been shipping and stuff, and assume I have a distribution center in Reno, Nevada, and I have one in Allentown, Pennsylvania, and I only ship by road freight, and it costs 2 cents per mile to ship, and I always ship from the nearest distribution center, except for iPhones, which always come from Reno. Okay, based on like my history, can you predict the shipping costs for the next 6 months as a percentage of my revenue, right? And can you do it like an exponential moving average and do a best line of fit with a gradient descent and give me a prediction and blah, 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 all this stuff. And it rattled off and did all this. It went and ran a whole bunch of queries in the database, got all the data, it did all the stuff, drew a lovely little chart, and so on. And I've got to say, it's quite amazing what these models can do today, right? The coding models, Doug and I, we both work a lot with these coding models like Claude Code, and I've been using Grok Code Fast 1, which is not as good. Yeah. But it's amazing just how good they are. I mean, I think that the coding ones are as good as like a junior developer that sort of can do a lot of stuff. They're kind of smart, but they won't see mistakes. Like, I wanted to check in my GitHub token into the source code. I'm like, no, don't do that. We don't do that here, for example. But, it's amazing. Like, a year from now, I imagine they're going to be fantastic. It's if you haven't played with any of these things, I would really encourage you to go and give them a try. It's quite amazing what you can do.
So the tool part is the access to the physical world. And so
Yes.
you don't write a tool to launch a nuclear missile.
Exactly.
Yeah,
Don't write a tool
exactly.
to launch a nuclear
Remember
missile.
that,
Actually, I think I have a tool thing. Okay, I do have a tool thing. So here's an example. This is the one I was talking about before with the check. Like, say, here's a product brochure with the types of accounts and the costs and stuff. You can see you ask it a question. Saving toward a house deposit. Oh, the question's not here. I think I asked it like, I want to save for a house. What sort of savings account should I get? And you can see it tell me the different kinds of accounts and so on. And this is called grounding. This is where you can have the LLM give you the reference. So instead of just giving you the answer, it says, and here's where I got that answer from, so that you can check, because they make stuff up, right? If they don't know, they just make it up. So it's very important to be able to trace back to where it came from. So when you do the similarity search and you get, this would have been the two that survived the re-ranking procedure, like it probably searched for the top 3 or the top 5 or something, and only 2 of them were actually relevant. And this is the most relevant and the second most relevant, and so on.
You would tag that as metadata when you do the search, or when you do the.
You put it in the system prompt. You say, like, after the answer, tell me, where you got the answer
when
from.
you did the chunking, you had to put it into the vector where it came
Yes.
from. You had to.
Yeah, the vectors are always associated with the chunks where they came from, because the vector by itself is useless, other than for the search. So once you know which vectors you're interested in, you go to the chunk. Yep. What else do I have here? Some other interesting stuff you can do is we do have a tool that can. So in Oracle, and I'm sure in other databases, they have like this catalog thing which describes your tables and your columns and all that. So you can say, I have a table called journal that contains information about pending and committed transactions, and here's the columns, and you can see it explains. So if you look at the catalog in Oracle, which is like another table, it tells you, if you bothered to do this, it tells you what the columns mean. And it might be like, here they're kind of obvious amount, but if your columns are like C1, C2, C3, the LLM can't do anything with that. I don't know what they mean, right? So if you do have a catalog, this kind of thing, then you can give that to the LLM, to the tool, it can generate it, and then it helps it to do things like it can, if you ask it a question like, what were my last 3 checks, then it's going to look at it and go like, okay, well, I have a tool that can go to the database and it has access to this table that has accounts and checks and blah, 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 and it can figure out from its general knowledge that you might be interested about the date and the amount, whatever. It'll construct a query, get the data, and format it as a table, all that kind of stuff. So, whereas this one here, it doesn't need to do a query. You can just get this from the vector search.
What is that for? I can't read it.
Do I have to keep a minimum balance in my checking account? So that one, it's gonna to the rag. Yeah. We also have in Oracle, I don't know if other databases have this. In Oracle, we have something called real application security, which lets you have rules about who can see what, basically. So you might say, people can only see their own transactions, so it's going to filter out other people's.
Oh.
Or, you're not allowed to see the control number for the check. You can only see the external check ID or whatever, blah, blah, blah. So you can filter rows and columns and space and all kinds of rules and stuff like that. And you can do that to a vector store as well. So if you have a vector store, you could say, customer service people are allowed to see these vectors, but supervisors can see these vectors, which maybe have more rules about when you're allowed to give a discount or a refund, or I don't know, something that only a...
When you say see the vector,
Yeah.
that means those vectors are still kind of come out of the first pass of
No.
similarity. No, they won't even
No.
come that far.
So when they
get filtered even
right
before.
in the database, because this is a problem, right? So if you rely on the LLM to filter the data, it's working on probabilities and matrix manipulation and stuff. Like, it doesn't understand what it's doing, right? It might do the wrong thing. It might give your social security number to somebody else or something, or the balance of your 401k account or something that you don't want people, or your health records. Like, it doesn't care.
At least in the RAG part, doesn't it embed the content with the vector?
Yes.
Right. So when you get the vector, you also have access to the content of that vector, so
mean
it
the
just
chunk,
returns it.
right?
Yeah, the chunk.
Exactly.
Yeah.
Yeah.
You also get, you don't get just a reference, you get the chunk itself.
Yeah, you
The
get the
chunk.
actual data.
Yeah.
Yeah.
Actual data.
So like
Oh, okay.
you
Yeah.
can see that when you like, play with it locally, like I do on my machine.
Yeah.
You populate it, you pull it, you can see how the vectors are all the numbers, and then there's the content.
But
So the
my
idea of
point
this
it
is-
gets filtered very early.
So we
This
do it-
restriction.
Yeah, so what we do is we filter it in the database. So when the LLM is connecting to make the query, like using the tool, it's going to go, Bob wants to know his 401k account balance, right? The database is going to go, okay, but you can only see Bob's, right? Because you are Bob, okay, that's fine, you're logged on, whatever, I'll give you that. But if Doug asked for Bob's social security or 401k account balance, he's going to get 0 results.
Unless
from
Doug
the
could
some-
administer and approve it,
Exactly.
has
Right, you can have
whatever,
roles
some kind
and-
of
Yeah, exactly. Yeah. So that's much more reliable, right? Because the database is not going to make a mistake about that,
That's enforcing them.
right? And the LLM is never going to get the data that it shouldn't give to Doug in the first place. So you're not relying on the LLM to do the right thing. You just, Yeah.
But that happens only because you're setting
you've got to set up.
security status.
Exactly.
There's no concept of, like an obfuscator or something like that. Or,
Yeah, we have all that too. Like, you can block out data masking and all that. You can block out certain columns and stuff. Yeah. You can do that.
Based on what?
Just whatever rules, metadata, RBAC, roles. Yeah.
And that's in the area of sort of standard DB
Yeah, that's standard.
interaction and manipulation.
Yeah.
I mean, certainly being used effectively by, as an agent tool.
Yeah.
But it's still, that part is all pretty standard
Right.
at this point. Okay.
Exactly. So that's like using like a real database like Oracle, which also can do a vector, as opposed to like a vector database, right? It has all of those capabilities, like all the security and transactions and stuff, backup, blah blah blah, sharding. Like, if you pick a specialized vector database, it's not going to have all that stuff, right? It's just a vector database and nothing else. What else do I have here? Blah, blah, blah. Okay. Time-wise, I was going to do a demo, but my demo environment totally died, so I'll just quickly run through. I have the backup videos. Yeah, cool. So this is showing you, like, you can configure different models. They can be public or self-hosted models, like we talked about. You can set the API keys, all that kind of stuff. Here you can play with the parameters. This is our recap. We've already talked about all this, but just to show you what it looks like. So you can pick the model you want to use. You can tweak the parameters. You can ask the questions, change the parameters, ask it again, see what it does differently, all that kind of stuff. This is an example of temperature, I think. See here, it went nuts and started giving, there's a Chinese character, there's an ampersand. See, it just went crazy because you set the temperature too high. This is prompt. You can play with the different prompts, and you can see these can be quite complex. This is like a whole art to itself of making the prompt good. So see, it's here saying, keep your answer grounded in the facts and the documents that were provided to you. For example, that's why you get the little boxes at the bottom. This is saying, if you have the chat history, this is an interesting one. It's saying, rewrite the question, right? So if say I'm talking to the model about, I'm taking this medication because I got hair growing out of my ear and I don't want that. Like, I'm taking this weird experimental medication. Like, what is it going to do to me? What are the side effects? Whatever, I don't know, or something. And it gives you some answer, blah blah blah. And then you go like, can I drink alcohol while I'm taking it? Right? If you do a vector search for can I drink alcohol while I'm taking it, you're going to get garbage, right? What's it? So we rewrite the question as well. So the model will actually rewrite the question, can you drink alcohol while you're taking whatever medication, blah, 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 and do a vector search on that. Because then you're going to get things that are actually semantically similar to what they're really talking about, right? You need to have memory for that.
Essentially sort of like mashing
The history with
history into the question.
exactly. Yeah.
Right? But it's doing it for you.
Yes.
The system is doing it for you.
Yep.
Instead of just carrying the history.
Yeah, the history it needs so that it can do reasoning. But when you want to do a vector search, it's no good searching for something that's similar to it, because you're going to get garbage, right?
Oh, I see.
So you need to
this is when you want to do like a single vector search.
Exactly. Yeah. So you would do that first. Like you rewrite the question, do your vector search, get your chunks back, then you would go and do the reasoning part of it to answer the question. Yeah. This is an example of cutoff, knowledge cutoff. I think here it said something like, oh, it's asking how do I do something in the database, and it doesn't know because it didn't exist when that model was trained. And then I ask it again with RAG, and it knows the answer because now it has access to the information from after the model was trained, for example. This is the loading screen. So here you can pick, those are some embedding models. Again, there's thousands of different embedding models. You can fiddle with the parameters of the embedding model, what kind of distance metric you're going to use, how big the chunks are, the overlap, all that kind of stuff, where the data is coming from, how you're going to read it, where you're going to store it, and so on. This is an example. You see it running here. And this is going to show an example of what the tables. So these are vector stores in the database. You can have lots of these, as many as you want. And you'll see an example here of, here's one. And here's the columns in here. So here's your metadata over here any minute now. You have an ID. Here's the chunk, see? That it pulled out of a PDF document in this case. And here's the vector. That's like a little piece of the vector. You see it's just a big long string of numbers. So here's an example with RAG enabled where it's going to ask the question, and you'll see it'll give references so that the answer is grounded in the facts where it got the answer from. There's the references. Those are the chunks, the most similar chunks from the vector search.
That whole thing about looking at the vectors, it's almost like, who cares?
Yeah.
I guess you're doing like
You
some
don't care.
spot checking.
You don't
just
care.
to kind of like see, but
Yeah.
it's like in the scheme of things, it's something that you wouldn't normally
Exactly.
spend hours focusing on.
Yeah.
Maybe at the very beginning, make sure you're sort of oriented right, but
Yeah.
very soon
If
you're
that
not
vector
looking
was
at that
chunk
set.
from like your intranet or something, you probably want a reference to the document where it
No,
came
but in
Yeah.
terms of like human beings as a
Yeah.
developer,
Yeah.
look, or an analyst looking at that particular thing that was 3 little
Yeah.
slices ago, it's not actually that useful.
Yeah.
Once
data-
you're sort of familiar with and things are underway, it's basically you're never really going to do
Right.
that part again.
And the
Yeah.
different embedding models will give you different vectors.
Sure.
Yeah, it
Like a
only
data-
means something to them.
A
Yeah, but
data
not to
scientist.
me.
Yeah,
Not
Yeah.
to me as a
exactly.
human engineer working with this stuff.
Right.
Yep.
Once, except as like first little baby steps to
Yeah.
kind of get familiar.
Right.
Once I'm at all accustomed to this kind of stuff, it's just
Yeah.
okay.
Like a data scientist might look at it because you would want to like maybe do dimensionality reduction and plot it to see the clustering to make sure that you have a good spread of the vectors and stuff and they're not all clumped together. But
Right, but they're still not looking at like one at a time.
No,
or
you would
small
look at the
little
whole
entire-
space.
They're looking at a whole
vector
space. And
space.
doing large scale analysis.
Right,
On that large,
exactly.
Your own data analysis.
Yeah.
Okay,
like an individual vector is basically meaningless. Yeah. Without the others. Like it's exactly. Like, if you'd only ever seen a Saint Bernard and you'd never seen another dog, how do you know if it's a large dog or not?
Because the vector tells me.
What is this one? This is the same question with a different model, and you see it's. This was asking for a code, and like, what's the code to do something or another, and it's giving the same code, but the answer is kind of a little bit different, and whatever. You see, it has bigger chunks than the other one had, and so on. So this just some sort of examples here. This is the evaluation piece. So here we're going to generate. So use the second LLM to generate a Q&A data set. So you see we pick which model we want to use, how many questions we want, and then it will generate. You have to give it the data as well, obviously, and it will go and generate the questions and then show you the questions, and you can fiddle with them, you can edit them, and all that sort of stuff, and then you can run an evaluation. So once we have the Q&A data set here, so you can see here's the question, the answer, where it got it from, and there's some metadata and all that kind of stuff. And then you can ask the question. So here you pick which model, whether or not you want to have RAG, fiddle with all the parameter settings, all that sort of stuff, run the evaluation, and it will come up with an answer. So this is going to perform probably poorly because it doesn't have access to the private information. 0% correct. There you go.
She's got the one question.
It got the
wrong.
one question wrong. Yep. Yep. Did you know that 73.5% of statistics are made up on the spot?
3%
That's a joke. Here's the same thing. See, we turn on RAG, so now it has access to the private corpus of information. I'm going to run it again, and this time it will do better. You know, in real life, you would never do this with one question. Obviously, you would do it with like 1,000 questions or something. But you know, it takes a long time. So that's an example of the evaluation piece. There's an interesting technique called auto-rag, which I think it was you asked about before. Why don't you just let another LLM fiddle with all of the settings and do this for you? That's called auto-rag. There's a lot of research papers out about that, which is definitely a thing as well, right? Using yet another LLM to figure out which ones to use to get the best results.
Well,
So,
as a human, I know I get caught in local minima quite frequently.
yeah. Oh, yeah. Exactly. All right. So that's all I had. What's the time? 27. We're doing good. I'll just shut up now, and you guys can do the wrap up, and we're good to go. So I hope there was something of interest in there for you.